But before we continue, we can return back to this code and see how we can store this result. There are many different ways, but the one that I chose in this case is to store it as step 3 coefficients. We do the linear model like in here, and we ask coefficients of this model to be stored as step 3 coefficients. So let's try this out. So remember, this was 9.83. I should also asked to show how this object would look like. Step 3 coefficients results in this named numeric vector where we can subset it to the second element of it to get the coefficient of in front of the residual of d. So this is something that we will introduce exactly when we try to convert all of this code into a function. So to replicate it 100 times, this time we are going to use a for loop. And we first initialize a vector, a numeric vector of length 0. But this object now exists, although it has length 0. What the purpose does it use? It will accumulate all the answers, all the estimates that we get for all of our 100 simulated datasets, and it will, in the end, append the results, the new coefficients, to existing results. As you know, for loop starts with the counter I, and we say for I starting from 1 and increasing by 1 until number of rows of our simulated nested dataset. We can also just say nsim, right? It's the same. So step 1, we need to. So basically, these 3 steps is just a copy of this code. Let's do it by step. So we copy this code and we have the dependent variable equals dataset y. But this time it shouldn't be dataset. We should use the object called simulated 100 nested column data, and then we should use the ith dataset. So depending on which iteration of the loop we are in. So we take this and we substitute all the mentions of dataset with this. Step 3 coefficients. Now we want to use this in here. We want to append to our results a vector that we created, the newly estimated double selection estimate. This is actually not needed, but this is a nice way to keep on track on which iteration your loop is, just in case something is stuck, your code is stuck somewhere. You will know that it's actually stuck somewhere, because it will print out that this is the first iteration, this is the second iteration, and so on and so forth, as the loop will progress. Then we transform the results CVDS that now will be populated, will be a numeric vector of length 100, and we create a data frame out of it. Why do we do this? Because then we can pass this object into the plot estimates function that we used before, that will plot the density function of the estimates. As you can see, we create the column called estimate here. And finally, we summarize the mean and standard deviation of the estimate. So now I run it, and it will take some time. This is okay. Finally, you will get this distribution of our double selection estimator that we run 100 times on 100 different samples from the same data generating process. Now, in fact, we are told to use rigorous lasso when we want to do double selection. We are told not to use cross-validation when we do not use cross-fitting. So we are using our lasso effect model, which comes from the HDM, high-dimensional matrix package, developed by the authors of the post-double selection estimation. Our lasso effect takes the usual form. It takes a matrix of potential confounders. It takes the vector of the outcome variable and the vector of treatment. And we should say what method we want to use. We want to use partialing out. In this case, it is partially out via post-lasso estimation, or double selection, which we discussed in the class. And finally, we can we ask the coefficients of this estimation based on the data set, the very initial data set that we used. And the estimate is very close to 1. Now you're asked to exercise and you show how would the distribution of the double selection estimator, or the partially out via post-lasso estimator, will look like if we apply it 100 times on our 100 generated samples. So first we're asked to define a function that estimates the post-double selection estimator. We just need to copy this code and amend it. How do we need to amend it? Now remember, it's inside a function and we're passing data called data. So it's not data set here, we should use data instead. Now finally, we need to get the coefficients of our result. Here is not result RLE, but we are saving it as matrix res. So we call it here. And we want, and I ask you to convert it to a data frame such that we again can use map DFR function. So we want the output of this function to be also a data frame at the end, such that we can just bind the rows of different data frames to collect all the 100 results. Okay, so now you can convince yourself that it works correctly. Let me comment out this part and put, let's apply this estimator last to DS on, again on dataset, not yet on the simulated 100 nested dataset. So estimator lasso DS, and we say data equals to dataset. And it should give us the same result as in here. My mistake was that I here did not put data Y and data D. Now we run, and yes, it gives you exactly the same answer, 101, as in here. Okay, now we are ready to go, to continue. So next thing is estimate the post-double selection estimator on all of the 100 samples. I'm putting here map DFR, and then what is the function that you want to apply? I want to apply estimate R lasso DS. I'm passing simulated 100 nested subset I.x in this case. Yes, this function will give us a data frame of result like this for each iteration, and map DFR bind the rows of data frames as a result of the mapping operation. Let's see the head of that operation. I probably forgot a closing. Yes, that's it. It takes time. And this is the first 6 rows of our results RLE. And you see, this is the estimate for the first sample. This is the second, this is the third, and so on. Finally, what we see here, since these are the results from an HDM package, they name their columns a bit differently from the standard way how standard length model would name. So that's why we should rename this column estimate dot into estimate. So we say rename estimate, which is a new name for the old name estimate dot. So after I do this, you would see how this will change. But then I also want to continue before running the code again, and then I would want to plot these estimates using plot estimates function. Remember, plot estimates function wants to find a column called estimate. That's why we did this step. And then we put results RLE. After that, we also want to see the usual summarize part. mean estimate, and standard deviation estimate. Now let's run the code again. And here are the results. This is the estimates of the rigorous lasso. The mean is quite close to 1.